Hi everybody. This is our first video for Unit 2, first for blended chemistry. And we're going to focus on some of the variables that we're going to measure and evaluate in terms of gases, and then look at some of the graphing and some of the patterns that we're going to see throughout the graphs. So we're going to go ahead and dive right in so this video isn't too long. First thing we need to know is that gas particles are in constant random motion. Okay, gas particles are constantly moving. If we think in terms of solids, liquids, and gases, solids are really closely packed together, very dense. Liquids have a little bit of fluidity and can flow around each other. Gases are really spread out. They take up the entire space of the container that they're in, and they're constantly moving, constantly bouncing off of each other. All right, one of the major variables that we're going to use to evaluate how gases are behaving is temperature. Temperature is a measurement of the speed of particles. Okay, specifically, it's a measure of what we call the kinetic energy, which stands for the energy of motion, right? As we increase the temperature of a sample of gas, the particles will start to move faster. And then the opposite's also true. As we lower the temperature of a gas, the particles will start to move slower, right? Particles only move in straight lines, right? They don't have a little pilot inside their nucleus and they get a zigzag and fly all over and around the container. They only move in direct straight lines until they collide with either another particle or the wall of the container, right? And we learned this last unit when we had to illustrate solids, liquids, and gases in particle pictures, but we need to remember that for all of these particles, we're going to draw them with the famous whooshie, right? That little tail helps us to illustrate that the particles are in motion and that they're flying in that particular intended direction throughout the container, right? So in terms of temperature, since we're going to adjust the temperature and ultimately the speed of these gas particles, we need to be able to illustrate the particles at different speeds. And so the tail, the whooshie, is going to help us sell that point. So one tail is going to represent a slower speed or a lower temperature. Two tails is going to represent a medium speed or a slightly higher temperature. And then three tails is going to represent a fast speed or an even higher temperature. Right? So if we had to illustrate a particle picture of gas being heated by a Bunsen burner at room temperature, we could illustrate three particles going a bunch of different random directions with one tail, and then if they're being heated by a Bunsen burner, we might draw them with two tails each. And they're now flying slightly faster throughout the air than they were before at room temperature. Okay, it's important to note that we have to illustrate each particle with the same number of tails within a box. All right, if I were having you all in the classroom, I couldn't selectively heat the back half of the class and keep the front half of the class cold. So when you heat up a container, all the particles are experiencing the same amount of heat. So we can't just go in there and throw a third tail onto one particle and leave the others with two. We have to make sure that all of the particles have the same number of tails. Okay? So the next variable that we're going to talk about is pressure, which you probably heard of in terms of like tire pressure or like your bike tire pressure. And pressure is specifically referring to the force of impact between particles and the container walls when they collide. So how fast and how often are the particles colliding with each other and the walls of the container that they're stored in? When we want to illustrate pressure using a particle picture, we're going to use this bent tail or bent whooshie, which is what we're referring to as a pressure event. All right, so this particle is drawn with a bent whooshie tail, indicating that it has collided with the edge of the container wall, indicating that the pressure has changed. So pressure events are really only important for when there is a change in the pressure. There might be some times where our pressure is being held constant and there's no need to draw the bent tail. So they don't have to be bent or drawn bent every time. Right? One of the natural areas where pressure does change is referring to the atmospheric pressure. If you've ever flown in an airplane and had the unfortunate experience of your ears popping, that's the result of the pressure of the air and the atmosphere around you changing. And so atmospheric pressure is a result, or is the amount of force exerted on an object by all of the air particles in the atmosphere. And so really it depends on the amount. The higher up in altitude or up in the air you go, if you've ever heard of like above, like at the top of a mountain, they say that the air is really thin. It's because there's fewer particles the further away you get from sea level because gravity starts to get weaker. All right, so the higher in altitude you go, the lower your atmospheric pressure, and the lower in altitude you go, below sea level, the greater your atmospheric pressure. So with this example over here to the right, if we are referring to something being above sea level, we're saying that this is low pressure. And if we're saying something is below sea level, we're saying that that is high pressure. So if I had a sample of 3 gas particles at a low temperature at above sea level, and I took it below sea level and I wanted to indicate that the pressure has now increased, I would draw these bent tails colliding with the wall of the container, indicating that these particles are now experiencing more pressure and colliding with the walls around it. Right? Now, it doesn't have to be one particular answer. I do want to continually reiterate that with these particle pictures. There's more than one way to draw these correctly, but the fact that we go from 0 pressure events in this box to 2 pressure events in this box has illustrated an increase in pressure going from above to below sea level. Okay. All right, on to the next page. We're going to talk about the variable relationships that we'll be analyzing. And so we've already talked about P in terms of pressure. Last unit, we talked about V in terms of volume. T is going to represent temperature, but N is a new variable that we're going to simply refer to as the number of particles. Okay, if we think in terms of like pumping air into a bike tire, we can increase the number of particles by pumping more air into it, and as a result, the tire gets a little bit larger, the pressure builds up inside the tire, and all the other variables adjust based on that change. Right? So the first variable that we're going to talk about in relation to pressure is volume. And so over here, we've got a pressure versus volume graph, and we want to remember that our graphs are always y versus x. So this is a P-V graph. And we actually did this in the lab yesterday. This is referred to as Boyle's law, and his experiments showed us that as the volume increases, the pressure decreases. So in terms of that syringe, when you pushed down and made the volume inside the syringe smaller, the same number of particles were trapped inside, but the pressure inside really increased. Okay? So when the volume decreases, the pressure increases. This is always referred to as an indirect relationship, and the graph that your computer gave you yesterday was a shape like that. So that's the classic shape of an indirect variable relationship. Okay? The next two we're going to talk about are referring to pressure versus temperature. And so if temperature is increasing and decreasing the speed of the particles, we can say that as temperature increases and the particles move faster, they're going to collide with each other in the walls of the container more. Therefore, the pressure inside is also going to increase. And the opposite of that is also true. If we cool the gas particles down, they slow down, they collide with each other less often, therefore the pressure will decrease. This is a classic direct relationship, because the increase or decrease of one variable has the same effect on the other. And graphically, this is always expressed as a straight line, a linear relationship. So as you increase along the x-axis, you increase along the y-axis. And then the last variable relationship that we're going to talk about is pressure versus the number of particles. And here again, we say that as the number of particles increases, like pumping air into a bike tire, the pressure inside that tire will increase. And as you decrease the number of particles inside a container, like if you get a flat and you get a leak, then the pressure of that bike tire also decreases. Another direct relationship, which means this is another linear straight line representation. Okay? The last little bit, I did want to go back to the pressure versus volume graph, just because sometimes when we get ready to evaluate this type of graph, it's oftentimes difficult to process what happens when you go from, say, point A to point B. All right. In terms of where you're at along the x-axis, you go all the way down. From A to B, you're actually increasing along the right. So from A over to B, your x value is increasing. But in terms of your y value, you're actually going down in the y-axis. So your y value is decreasing. Okay? Oftentimes it's helpful to draw little dotted lines back to your axis so that you can figure out and evaluate how those variables are changing from one point to the other along the graph. And you'll see that as you go through your homework here in a little bit. Okay, so just a reminder, your homework will be posted to Google Classroom. It's another worksheet. And if you have any questions as you go throughout this, even as you're watching this video, please don't hesitate to swing by my classroom or shoot me an email anytime. Okay, thanks, guys.